Hey there, welcome back to Short Text 331. Today we're going to continue our discussion of eigensystems and inverses. So this is part 2. If you haven't seen the previous video, go ahead and take a look at eigensystems and inverses and then come back to this one. Now, to continue this discussion and recap a little bit of what we discussed in the previous video, consider a matrix A that is normal, and that is a matrix A such that A dagger A is equal to A dagger. In other words, A commutes with its dagger. And in that case, we have a theorem that guarantees that A is unitarily equivalent to a diagonal matrix D. And what that means is simply that U dagger A U for certain matrix U is equal to a diagonal matrix D that's made out of the eigenvalues of our matrix A. And remember that U being unitary, this unitary transformation that we have here means that U dagger is equal to its inverse. So if you have U, then the inverse is simply obtained by taking the dagger, so transpose complex conjugate. And in this case, the matrix U is made out of the eigenvectors of A organized in columns. So the first column of U is the first eigenvector of A associated with lambda 1. The second column of U is the second eigenvector of A associated with lambda 2, and so on and so forth. Now, if you put U and U dagger on the other side of the equation here, which you can easily do because you know that U dagger is the inverse of U, then we have the so-called spectral decomposition or spectral representation of A, which takes this form U, D, U dagger. And so A is a matrix that we can write in this way. The matrix of eigenvectors, the matrix D of eigenvalues, and the matrix of eigenvectors daggered. And if you write that in detail, so that means the matrix elements of A, ij, are given by the sum. So the sum from k equals 1 to n, so if n by n is the size of our matrix, and a product of eigenvector component I, eigenvector component j over here, star, and then the eigenvalue lambda k in between. The same type of representation you have for the inverse of A, if A happens to be invertible. It could very well be that A is not invertible, by the way. The fact that it has eigenvalues and eigenvectors and is unitarily equivalent to another matrix D, like we saw here, doesn't mean that A is invertible. It has to also be that the eigenvalues are non-zero. But if that's true, if none of the eigenvalues are zero, then A is invertible, and we can write A inverse element ij in this way. So it's basically the same type of expression that we saw before, and it comes from this from here, from this spectral decomposition. So it's eigenvector k element I, eigenvector k star element j, and then lambda k inverse sandwiched in between, and sum over all k's from 1 to n. Now, we can learn a little bit more if we notice that A inverse or A inverse A has to be the identity. And so that's what we're going to explore next. You see that A inverse A has to be the identity matrix, and the identity matrix has elements given by this Kronecker delta ij. So that is to say, when I is equal to j is equal to, when I is equal to j, then the result of this is 1, and when I is different from j, the result is 0. And so it must be that delta ij is the result of A inverse A element ij. So we go ahead with that calculation. So in terms of the definition of the matrix product, we just have the sum over q from equals 1 to n. And so we contract this index q, and we have the outer elements, the outer indices I and j associated with the result. And now we can insert our expression for A inverse and A in terms of the spectral representations that we saw before. And that gives us this big chain of stuff. But let's unpack it. Let's see what it does. So the sum over q, I just copied it. Then this element of A inverse is written here in the middle. And then this element of A is written here at the end. And now what we see by carefully looking at this expression is that q appears here in the sum. It doesn't appear anywhere except here then, and then here. And so what we do is we go ahead and we pull this sum in all the way to here, and we capture also this q here. And if you sum over q these two objects, you see that you have to obtain delta kk prime, because that is the dot product of vk star with vk prime. And so we know that the eigenvectors of A, because A is normal, have to be orthonormal to each other. And so that's the same as saying that the matrix U is unitary, which we assumed already, again, because A is normal. And so that simply means that the result of summing over Q over this object times this object has to be equal to delta k k prime. If this sum in the middle bothers you, just think of it as pushing this through the sum. We can do that. This doesn't depend on k prime at all. And this q here is not touched by anything, so we can push that together with this into the sum and do that calculation. So what I underline here in green then is an operation you can go ahead and do, and that gives you delta k k prime. So okay, let's write that down. So then we're left with the sum over k and these two factors, vk and lambda k inverse, and we have the sum over k prime, and we have lambda k prime and vk prime star over here, and then delta kk prime. I just copied the result of the underlined stuff here in green. And so now that we have this delta kk prime, now we're in a position where we can do the sum over k prime. And it just means that wherever you see k prime inside that sum, you have to replace it with k. That's basically what the Kronecker delta does. It tells you throw away all the k primes, replace them with k. That's what this operation means when you sum over k prime. And so we go ahead and we do that. And you see that something really cool happens where this lambda k inverse will cancel with this lambda k, which is prime now, but it will not be prime after we're done doing this sum. And then this vk prime star will become vk, and so we're left with this identity. And this, then, the sum over k of vk star, and element ij is a little bit like what we used before. It's a little bit like orthogonality, except it's not, because we're not summing over the elements, we're summing over the vectors now. We're summing over the vector index. So it's a different type of sum, and this is not an orthonormality property, it's actually a completeness property. So then the sum over k equals 1 to n of the summing over both vectors with the same index for the vector but different index for the element of the vector, giving us delta ij, is something we call a completeness relation. So what does that mean? What is that completeness? And so I will tell you about that next. So why is that called completeness, and what does it mean? So I'm rewriting here the expression that we had before. Delta ij is the sum from k equals 1 to n of vector element k, kth vector element I and kth vector star element j. So suppose we take an arbitrary vector w in our space. So then, of course, trivially, multiplying the identity by the vector and taking that the ith element is just the same thing as taking the vector and taking the ith element. The identity doesn't do anything. However, this identity is something we can write as delta ij, like I do here. And so now I've omitted the limits of the sum, but the sum is always going to be from 1 to n. And so 1 times w is the same as doing this sum of over j, delta ij, element j. And this is going to give us always just the ith element of w, because this is the free index that we have here, the I. And so we haven't done anything, but now I get to rewrite this delta ij in terms of this completeness relation that I have here to try to elucidate what this means and why it's called completeness. So we go ahead and we insert that in here, and we see what we can do next. Well, we have sum over j from before and sum over k that we just inserted, and so now we're going to flip the order of the sums. Again, these are finite sums, so that we can do that with impunity, no problem at all. So we go ahead and we do the sum over j, and what does that sum capture? Well, it captures this guy because there's a j here, and there's another j here from w, and so that gives us as a result a sum over k. That's the only sum we have left over, vk element I times b sub k. And this b sub k we have defined as the sum over j that we just did. Sum over j, vk star j, wj. And so what that tells us then is that we can write our vector w as the sum over k, all the eigenvectors that we were dealing with before, the eigenvectors of our matrix A that we left in the previous page, times some coefficients. Okay, so and this vector w was arbitrary, and so that's great. That tells us that because of this completeness relation, we can write an arbitrary vector as a linear combination of the vectors in our space. These vectors, the eigenvectors of our matrix A. So w can be written as a linear combination of the vk eigenvectors with some coefficients bk, which are to be computed in this way, as shown up here. So you have to do this sum, which is nothing other than an inner product. This is the inner product of vk with w, and that's how you compute the bk's. But by virtue of our completeness relation, then any arbitrary vector can be written in this way, which is sort of something that we sort of already knew. We knew that our vectors vk are not only linearly independent with each other, but they're also orthonormal, and we also knew that they're bases. So that the fact that they're bases is really reflected in a way here in this property, meaning that they are complete. They form a complete set, and not only that, the fact that they're also orthonormal tells us that the coefficients bk can be calculated in this way. So orthonormality and completeness sort of go hand in hand in this case, when you have a complete set of vectors, which is what we have here. So in the example that we saw in the previous video, this property is something you can write explicitly, the property of orthonormality and completeness. If you recall, in that example, we analyzed this operator A, which is minus the second derivative, and we studied functions, or rather we imagine applying that operator in a space of functions that vanish at 0 and vanish at some point L. And so these functions live here, and of course we're assuming that the functions are twice differentiable, at least, and so we can apply this operator in a meaningful way. And we saw then that the eigenvectors take this form: some constant times the sine of k pi over L times x, where that k is a number that goes from 1 to infinity, an integer, and then lambda k is k pi over L quantity squared. And so these are the eigenvalues and these are the eigenvectors. So in terms of those eigenvectors and eigenvalues, the property of orthonormality is this: is that the integral from 0 to L of psi k star of x, psi k prime of x dx is delta kk prime. So this is a kind of inner product, as something we've seen before. And if you haven't seen the video on inner product, you should go check it out. This is a kind of inner product, is perfectly well defined. And if you do this calculation for these objects, you will see that indeed that gives you delta kk prime. And so that's orthonormality. Completeness here is very different. It's a sum, as we saw before. It's a sum over the index in the eigenvector itself, not the element of the eigenvector, but the index on the eigenvector itself. And so, in other words, the index that runs over the different eigenvectors, not the index that runs over the elements of a given eigenvector. And so completeness here reads as the sum from k equals 1 to infinity of psi k of x, psi k of x prime. So we're looking at two different elements, or rather two different indices, or elements of a given fixed eigenvector k, and then we sum over all the eigenvectors, and that gives us the Dirac delta of x minus x prime. And this is then what we call completeness when we have this type of space of functions. That's it. That's all I have for you today. If you enjoyed this video, if this helped you understand any kind of material that you're working on, feel free to like and subscribe. And if you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a message in the comment section below. And I will see you next time.